Hello everybody. In this lecture I would like to show solve the following problem. Namely, I would like to find out the number of ways that the faces of a cube can be numbered from 1 to 6. So I would place the numbers 1, 2, 3, 4, 5, 6 on the faces of a cube. This is a standard math counts problem, I would say. So because of the rotational symmetry, the first number can be put in any way, right? So, and it will not change the count. So let's say that the bottom face has a 1, and then the die is put on a flat table. So we have already used 1 and it didn't increase the count. Then opposite 1 we can place a number in a unique way, right? So, well, in 5 different ways, I should say. Sorry for that. So times 5. And finally, we have 4 side faces remaining and 4 numbers remaining. So those numbers can be put in, because it's circular permutation, it is 4 minus 1 factorial, which is 3 factorial, 6 ways. So therefore the final count would be 5 times 6, which is 30. So the die can be, the cube can be numbered from 1 to 6 in 30 different ways. Well, the real cube, the real die is as you know, it is numbered in a unique way, obviously, but we are considering any numbering, right? I think in today's world, there's a 1 at the bottom, and then 6 opposite the 1, 1, 2, 3, 4, 5, 6, and then 2, 3, 4, 5 in some order, I forgot how. They are probably 2 and 5 are opposite each other, 2 on one side and 5 opposite the other side, and then 3 and 4 opposite each other. 3 here and then 4 here, because, well, yeah, the sum of opposite faces should add up to 7, I guess. But anyhow, so we can easily prove this result also using Burnside. So using Burnside, again, we have the cube. If you watched our earlier video, you realize that the cube, the symmetry group acting on the cube has how many? I think we established it has 24 elements in it, right? So 24. Please check my video about painting the faces of a cube. But if G is 24, and now we have the numbers 1 through 6, 1 up to 6, so therefore the number of orbits, in this case our orbits is not the coloring but the numbering. So number of numbering, okay, from 1 to 6 is equal to 1 over 24 times the summation of the fix of G is in G, and this is simply equal to 1 over 24, open parentheses. Let's start with the fix of E, the identity. So if you have a die which is already numbered, well, how many different ways can it be numbered, right? Because the fix of E, how many of these numberings will be fixed by the do nothing group member is all of them. So 6 factorial ways, right? So that would be 6 factorial. 6 factorial plus pretty much, well, not pretty much, all the other rotations of this shape, because we have 6 numbers given in a unique way, will create a new die, right? So there's no way that I apply a 90 degree or a 120 or 180 degree rotation and I get the same die in the same shape, right? So all the others will contribute simply 0, and that's it. Believe it or not, so that's just 6 times 5 times 4 times 3 times 2 times, times 1 all over 6 times 4. The 6's cancel, the 4's cancel, again 6 times 5, 30 different ways to number the faces of a die, and that solves our problem. Hope to see you guys in our next video.